A prism is an optical apparatus made of transparent material with flat and polished surfaces that refract light. The most commonly used prism is a triangular prism which has 2 triangular and 3 rectangular surfaces. The 2 rectangular surfaces through which light is refracted are called the refracting surfaces of the prism. The cross-section of a prism that is perpendicular to the refracting surfaces is called its principal section. Here, ABC is the principal section. The faces AB and AC represent the 2 refracting surfaces. The angle between the 2 refracting surfaces is called the angle of the prism or the refracting angle. Let us derive the expression for angle of deviation for triangular prism. Consider a light ray PQ incident on the refracting surface AB at an angle of incidence I. Let NN' be the normal to the surface AB at Q. The ray of light refracts at the face AB and QR represents the refracted ray. Let the angle of refraction be R1. The refracted ray QR is incident on the refracting surface AC at R and emerges along RS from the prism. Let NN" be the normal to the surface AC at R. For refraction at the surface AC, let the angle of incidence be R2 and angle of refraction be E, which is also known as angle of emergence. The angle between the incident ray PQ and the emergent ray RS is called angle of deviation D. In the quadrilateral AQNR, angles AQN and ARN are right angles. Hence, angle A plus angle QNR is equal to 180 degrees. Let this be equation 1. Since the sum of the angles in a triangle is equal to 180 degrees, in the triangle QRN, R1 plus R2 plus angle QNR is equal to 180 degrees. Let this be equation 2. From equations 1 and 2, we can write that angle A is equal to R1 plus R2. Since angle A is the refracting angle of the prism, we can write that refracting angle A is equal to R1 plus R2. Let this be equation 3. In the triangle MQR, angle MQR is equal to I minus R1 and angle MRQ is equal to E minus R2. Since in a triangle, external angle is equal to the sum of the 2 opposite internal angles, for the triangle MQR, we have D is equal to I minus R1 plus E minus R2, or D is equal to I plus E minus of R1 plus R2. On substituting the value of angle A from equation 3, we get D is equal to I plus E minus A. Let this be equation 4. Since the angle of refraction depends on the wavelength and refractive index of the prism, we can say that the angle of deviation D depends on the refractive index of the prism, wavelength of the incident light ray, refracting angle of the prism, and the angle of incidence. The angle of deviation increases with increase in the refractive index of the material of the prism. More the wavelength of the incident light ray, less is its deviation. Experimentally, it has been found that the angle of deviation decreases with increasing refracting angle. If the variation of the angle of deviation is plotted against the angle of incidence, the graph is as shown. As the angle of incidence increases, the angle of deviation initially decreases, reaches a minimum value, and then increases. The minimum value of deviation is represented by dm and is known as the angle of minimum deviation. Hence, corresponding to any value of the angle of deviation other than dm, we have two angles of incidence. These two angles correspond to I and A. That means, if one is the angle of incidence, the other will be the angle of emergence. Interchanging I and E does not make any difference to the value of deviation d. If PQ is the incident ray, then RS is the emergent ray, and if light enters the prism along SR, it emerges from the prism along QP. If the incident light strikes the prism at an angle that makes the deviation minimum, then the prism is said to be at its minimum deviation position. When the prism is placed at its minimum deviation position, it is found that the light ray passes through the prism symmetrically and is parallel to the base. In this case, the angle of incidence, I, is equal to the angle of emergence, E. Because of the symmetry, we can also write that R1 is equal to R2 and let them be equal to R. Hence, when the prism is at its minimum deviation, equation 3 can be written as A is equal to 2R or R is equal to A by 2. Equation 4 can be written as dm is equal to 2I minus A or I is equal to A plus dm by 2. But the refractive index of the material of the prism, N21, is equal to sin I by sin R. On substituting the values of I and R from equations 5 and 6, we get N21 is equal to sin A plus dm by 2 by sin A by 2. Let this be equation 7. Using equation 7, the refractive index of the material of the prism with respect to the surrounding medium can be found accurately. In this method, the values of A and dm are found experimentally. If the refracting angle of the prism is small, then the value of the minimum deviation is also small. But we know that for small angles of theta, sin theta is approximately equal to theta. Hence, we can assume that sin A plus dm by 2 is approximately equal to A plus dm by 2, and sin A by 2 is approximately equal to A by 2. Substituting these values in equation 7, we get N21 is equal to A plus dm by 2 by A by 2. On simplification, we get dm is equal to A into N21 minus 1. Therefore, for prisms of small refracting angles, minimum deviation is small and is independent of the angle of incidence.